started looking at rings the last time. We didn't get real far, so I don't know that anybody would have looked at any of the problems to have questions yet, because they're things we haven't talked about. But any kind of questions before we keep looking at rings? Rings is certainly one of those words in math. I wonder who came up with that idea. It has so many other meanings in English that I mean, group at least I can see. There's sort of a relation. English group is a collection of things, but ring, I'm not quite sure why they came up with the name ring. So we had looked at, I think, a couple examples. Let's think of some other examples, or list a few other examples. So, Zn, the integers modulo n, clock arithmetic. We've talked addition, we've also talked multiplication. It actually is a ring. Under addition, it is a commutative group. The multiplication is distributive, so that's a ring. One we've not really looked at much would be z parenthesis x, essentially the polynomials over the integers. So things like 1 plus x, 3 minus x squared, etc. As long as the coefficients are integers and we have polynomials, the claim would be, well, that's a ring. In terms of thinking about the group, what's the additive identity? Is there polynomial? Yeah, it's still 0. I mean, in a sense, 0 is 0x. 0 is a polynomial. Add it to any other polynomial, you don't change it. The distributive property holds. In fact, we use that quite a bit, even as we work with polynomials. So, that's an example. Let's look, say, at the integers, kind of build on this. So instead of kind of appending x and powers of x, we're going to append the square root of 3. So things like, things of the form a plus b square root of 3, where a and b are both integers. Now you may wonder why in the polynomials we go a plus bx plus cx squared plus dx cubed, where all the coefficients are integers. Why do we stop with just a and b when we talk z root 3? What's root 3 squared? 3. What's root 3 cubed? 3 root 3. So there's no point in writing, we could go to root 3 squared, root 3 cubed, root 3 to the 4th. They all get combined into here. If we add two elements of this form, are we going to get another one of this form? Yes, so the addition's closed. Multiplication being closed is not quite as obvious, or maybe not obvious at all. So if we say take a plus b root 3 times c plus d root 3, multiplying like we do polynomials, we get what, ac plus ad root 3 plus bc root 3 plus bd times 3. And if I rearrange, I get ac plus 3bd plus ad plus bc root 3. Is it of the right form to still be in the set? If we started with everything integers, That is still an integer. That is an integer. So we do get another element of the form, some integer plus some integer times the square root of 3. This set, in fact, would be what's known as a subring, because there's a bigger ring that's contained in the ring of all real numbers. I don't think we've got that much time to look at subrings. It's one of the many things we're going to kind of skip as we work through this, but sometimes special looking rings are of interest for us to look at. Now, let's think of a couple other things. Let's say the even integers. So 0, plus or minus 2, plus or minus 4, etc. Under addition, is that going to be a commutative group? Do we have an identity? Does every element have an inverse under addition? And is the addition commutative? It is. Does that operation work for multiplication? If we multiply two numbers from that set, do we stay in the set? Yes. Yes, we do. Multiply two evens, you'll still get an even. We're going to stay in the set. It is distributive. The multiplication is distributive over the addition, and so it meets all the properties to be a ring. So there are lots of rings. Trying to think of something that maybe just a group. The permutations. You know, we were rotating triangles, and those permutations. There we just have one operation. And I'm sort of at a loss to think of what would be another operation we could use. So to be a ring, there has to be two operations. One is called addition. It may not be our typical addition. One is called multiplication. It may not be our typical multiplication. Some of the problems I ask you to look at, we modify what the addition is and what the multiplication is. In fact, another example that I think we've looked at a little bit. Let's consider the set of all subsets of A. So we've got some set, and we're going to look at all their subsets. We could define x plus y as being, let's see, the union of x and y minus the intersection of x and y. I think we talked a little bit about sets. The reason we don't want just the union is that there's no identity with just the union. Or maybe invert. Well, we have trouble with I think it'd be inverses. With just the union, any set, union, the empty set, would be the same set. But there's no way to combine any set with any other set to get us to that identity. Whereas with this addition, the empty set is still the identity. X union the empty set is X. X intersect the empty set is empty. Take away the empty set from X, you do get X. So the empty set does work as the identity. What would work as an inverse for X? If we're going to take X plus X inverse and come up with this empty set, what set do we have to use here? to get us to the empty set. I think it has to be X itself. X union X is X, take away the intersection. That does get us the empty set. So each element is its own inverse. I think that's sometimes referred to as a Boolean set. Multiplication, X times Y. I think we use the X intersect Y. Intersect two sets, you're going to get another set. Proving the distributive would be quite a challenge here. But this is another example of a ring structure. Another example of a ring structure would be, say, the integers cross the integers, the set of all ordered pairs, A, B, where A and B are both integers, provided we define our addition AB plus CD, we just add like terms, and AB times CD, we multiply the corresponding components. So we combine the first terms with the usual addition and the usual multiplication to get our addition and multiplication for the new set. So there are lots of structures out there that are rings. In a ring, we would typically call, then, since they're under addition, it is a group, we know there's an additive identity. What do we typically think of when we think of additive identity? Does it have a name we normally give it? What do we do in the integers? What's the additive identity in the integers? 0. So we're still going to call it 0, even if it may be something other than our typical 0. We're going to call that the 0. There may or may not be a multiplicative identity. That's not required. If there is, rather than call it 1, we're actually going to call it unity. And again, there doesn't have to be an additive identity or multiplicative identity, but there might be.
There has to be an additive.
There has to be an additive identity. For it to be a ring, we have to have a group under addition. So there has to be an additive identity. But under multiplication, all we need is the multiplication close, so it really is an operation, and that the multiplication is associative, and that it distributes over the addition. Now, of the examples we've looked at, I think we've seen just one that doesn't have a multiplicative identity. Identity. In the evens, 0 plus or minus 2 plus or minus 4, multiplication-wise, is there anything we can multiply by any element in that set and not change it? Well, 1, but it's 1 in that set. So maybe I should say, is there anything in the set that that works that way? And so here's an example of a ring without unity. We're much more, I think, familiar with rings with unity. If I go back to this example, what in this example do you think the unity might be? Or is there a unity? Is there an element I can multiply by any other that isn't going to change it? One, I mean, ones are involved, but we're using here ordered pairs, so we need an element from the set of ordered pairs. So we need an ordered pair of something. So 1 and 1. 1 times A will be A, 1 times B will be B. The ordered pair 1, 1 will work as a unity. Or in fact, the unity. Much as we saw with groups, if there's one element that works as an identity, there's only one. Can't be two. I think we proved that. Combine the two candidates for unity, what are you going to get? Well, you only get one result. And you could call it the first unity or the second, but it's the same result. So you really can't have two different unities. So if there is a unity, we in fact call it the unity. Now, depending on our ring, there's another interesting thing that we might encounter. So if we're working, say, in Z, well, just first in the integers. If A times B equals 0, do we know anything about A or B? One of them has to be 0. What about in, say, Z12? If AB equals 0. Is there any way we can get a product of 0 in Z12 without one of them being 0?
Yeah.
I see some confident yeses. Somebody give me an example? 3 and 4. So in this case, 3 and 4 are both called divisors of 0. Because there is a way to take 3 times an element that's not 0 and end up with 0. What about in this Z cross Z? If we've got 2 elements, and I'll go ahead and write it AB times CD equals 0, 0. Do we necessarily know anything about one of the ordered pairs? Maybe I should be more specific. Does one of the ordered pairs have to be 0, 0? Or is there another way?
Split up between 2.
So what do you mean split up between 2?
So instead of A, B being 0, 0, A could be 0, and D could be 0.
So like 0, B, and C 0?
Yeah.
And that would give us 0, 0. So again, we could have divisors of 0. So in some of our rings, it's possible to get divisors of 0. In other rings, the only way to get a product of 0 is if one of them has to be 0. And this characteristic we make use of all the time. In algebra, solving quadratics. We factor, get the product 0, we know one of them has to be 0. So we use that rule, that idea, the 0 product rule all the time. It does work in the numbers we typically work with. There are other rings, though, in which it does not work. Those rings are actually given a special name. An integral domain is a commutative ring with unity that has no non-zero divisors of 0. And again, to be a divisor of 0, we've got to be able to multiply something other than 0 to get 0. So 0 is a divisor of 0, because 0 times anything would be 0. The question is it possible to take two things, neither one of them 0, and get 0? If we can, those would be divisors of 0. We also are required to have a unity. So even though the evens doesn't have any divisors of 0, it would not be an integral domain, because it doesn't have a unity. So there are a couple things that are needed. It also needs to be commutative. The only example we've talked about in terms of rings would be, say, 2 by 2 matrices. There the multiplication is not commutative. We're not going to do a lot with those, but that is an example where it's not commutative. But there is a unity. There actually is an identity matrix that could work as well. Yes?
Can you explain the no non-zero? So you're saying it can be 0, or it's a dummy?
Well,
I'm confused on that.
okay. 0 is always a divisor of 0.
Uh-huh.
The question is anything else?
So it's just non-zero, or no non-zero?
Yeah, no non-zero. So this one is not an integral domain, because it has some divisors of 0 other than 0 itself. So maybe I could, the only divisor of 0 is 0. Is 0 itself. Does that make it clear when I say no non-zero divisors of 0? Which actually brings up another thing I wanted to look at. Certainly in all the rings we're used to talking about, if we take any element times 0, we do get 0. Well, we're very used to that. 0 times anything gives us 0. Does it have to work that way all the time? Just because that's what we usually see, as we get things more and more abstract, in a concept, if all we know is we've got a ring that has a 0, is this always going to hold? Could we prove it? And if so, well, what's that proof going to look like? Because this is certainly a property we're used to working with the numbers we work with. Take anything times 0, you get 0. And in fact, most of the numbers we work with, that's the only way to get 0, because we're used to working with integral domains. The only way to get a product of 0 is to have 0, but we have seen on the 12-hour clock or some other clocks, there is a way to get a product of 0 without either one of them being 0. So there are some things where we have a commutative ring with unity, but we have some divisors of 0 other than 0 itself. So they don't meet the condition to be called an integral domain. So let's look at this. So I should probably put in a little bit more here. So prove if we have a ring A and any element in A, then A times the 0 equals the 0. Can we prove this is the case in any ring purely on the basis of we're working with a ring structure? Because we don't know what the set is. For that matter, we don't know what the operation of addition is. We don't really know what the operation of multiplication looks like. For that matter, we're calling the identity 0, but it may or may not be what we normally think of as 0. It just has the properties of being 0. So all we really know about this is there is an addition. There is a 0 for that addition that we called 0, and there is a multiplication. And the multiplication is distributive over the addition. And so, as we first sort of look at this, we may think, I don't have nearly enough information here to even begin to think about this proof. How am I going to prove that A times 0 when I don't know what the elements look like, I don't know what the multiplication does? How are we even going to begin to do this? Well, we start thinking through some of the things we do know. I just kind of went through the list. We do have a ring. So there is an addition. We don't see that. But under addition we have a group, so there is a 0. The 0 does certain things for us. 0 combined with any other element doesn't change it, but I'm not seeing any other element here being combined with addition. In fact, addition's not showing up anywhere here. The multiplication is distributive over addition, but again, I'm not seeing any addition here. Well, since most of what we know about 0 relates to addition, not multiplication, and we don't have any addition, is there any way we could get an addition in here? Is there anything maybe we could replace with something that involves an addition?
Did we say A times 0 equals A minus A?
I don't think, well, and even minus would be A plus the inverse of A. A does have an inverse. A plus the inverse of A is 0, but I'm not sure that we necessarily know how that's related here. Would you agree that 0 is 0 plus 0? 0 is the identity. The identity add anything doesn't change it. And what we're doing here is there are lots of other places in math we sort of take this plan of attack. I need a certain form. What can I do to get it in that form? Completing the square. We decide what we need to add and then we take it away later. Or center of a circle is x minus h. Well, we've got to say x plus 1. We write it as x minus a minus 1. So we've got it as x minus something. So here I'm just looking to do that. But at least now I do have an addition in there. You mean, well, how in the world does that really help me? Do I know anything about that? We can distribute. At least with an addition, we can distribute. So this is A times 0 plus A times 0. is. So we know that, right? Anybody see anything we could do there?
Keep doing that infinitely. I don't know if that really helps, but.
Could you subtract one, like on the other side?
Okay. Could we subtract one? Technically, no, we only have addition. But what is really subtraction? Adding the inverse. So we can add the inverse. You may think, I don't know what the inverse is. But it is an element. We have a ring, a times 0 is something. And it has an additive inverse. Every element does. So a times 0 is an element of A and has an inverse. And so let's add that inverse to both sides. So a times 0 plus a times 0 plus the inverse of a times 0. And what does that do for us? Well, any element plus its inverse is 0. That's what we mean by the inverse, right? And what about over here? Well, any element plus its inverse is 0, and so we get a0 plus 0. 0 is the identity. Wait a minute, wasn't that what we were trying to prove? That a times 0 had to equal 0? We started off not being really sure what it might equal, and did kind of the only thing I could think of to do, like let's replace 0 with 0 plus 0. Because 0 is the identity, I need to see some addition somewhere. And I didn't have those as I was starting. So I worked to kind of introduce an addition. Then I could use the distributive. Then I could use the fact that, well, we have additive inverses. And I've got the identity. And then realize, wait a minute, that was what I wanted to prove. So no matter what ring we happen to be in, whatever the 0 happens to look like, you multiply the 0 times any other thing, you're going to get the 0. Even in things that are not integral domains, I mean z cross z, you multiply by 0, 0, you will get 0, 0. There are other ways you could get a product of 0, 0. But if you use 0, 0 in there, you will get 0, 0 out of the product. So the question for the integral domain is, to get a product of 0, is the only hope to use 0? Or is there some other way? If there's some other way, then we don't have an integral domain, and things get a lot more complicated if we don't have an integral domain. Things are much more predictable if we have an integral domain. Let's see, there's one other structure that we can add in here. It starts about the same way that an integral domain does. And this structure is known as a field. Is a commutative ring with unity that has multiplicative inverses for all non-zero elements. So the integers is not a field. There are all kinds of elements in the integers that don't have multiplicative inverses in the integers. In fact, one could say part of the reason we have moved to the rationals is to fix that problem. Under multiplication, we want to multiply two numbers and come up with one, the identity, the multiplicative identity, or the multiplicative, the unity, and just in the integers we can't do that, so we come up with some new ones. And so the rationals is a field. Now you may be kind of wondering, why exactly do we exclude 0? I mean, wouldn't it be nice if 0 had an inverse as well? Well, it might be nice, but as this theorem points out, it's impossible. There's no way to get 0 times anything and come up with a multiplicative identity. In fact, the multiplicative identity, unless there's just one element in the ring, the multiplicative identity has to be something else. It can't be the 0 can't also be the multiplicative identity. Again, very much for this reason. Because a times 0 is 0, there's no way a times 0 can be a. Unless we only have 0 to work with. So 0 is a very special number. We kind of knew that, but it is a very special number as the multiplicative identity, or excuse me, the additive identity. A little bit more about one other example. One we've not done a lot with, but works fairly well, the complex numbers. The form a plus bi, where a and b are both real numbers. If I add two complex numbers, a plus bi and c plus di, am I going to get another complex number? Okay, I hear a no. Wasn't very confident, but I heard one.
Yes.
I hear a yes. Well, we'll get to multiplication, but, so, I mean, how do we typically add these? Yeah, we add like terms. So a plus c plus b plus d I. We add like terms and we regroup. We do get some real number plus some real number times I. So addition is a legitimate operation on this. Is there an identity? What can I add a plus bi to get a plus bi? Is there an element I could add?
0 plus 0i?
Yeah, I mean, we would just call it 0. We got 0 plus 0i. There is an identity. Are there inverses? Additive inverses. A plus bi. What could I add to get 0 plus 0i? opposite, both of these, so minus I plus a minus bi. Other ways we might write it, but that's going to work, so there are inverses. So under addition, this operation is a group, and it's commutative. The order I put A plus B, A plus BI and C plus DI, I'm going to get the same thing. And for commutative, again, it's the order of these two. We're not thinking is A plus BI the same as B plus AI. A plus BI is our one element. And it doesn't matter the order in which we add these two, we're going to get the same result, because this addition is commutative. So we do have an additive group. Now let's think about multiplication. Because you were thinking multiplication had a problem.
Yeah, because if you multiply two i's, it's negative 1.
Okay. So we get, if we multiply this with the FOIL technique, we get AC plus ADI plus BCI plus BDI squared. And you said that's -1, right? And minus BD. Which we rearrange and regroup. AC minus BD is a real number, and AD plus BC times I, that's also a real number. It actually is okay, an acceptable form. We multiply 2 of this form, we get another one of the right form. Some real number plus some real number times I. Don't think we'll look at the distributive. It turns out this is distributive over the addition. Is there a unity? Is there multiplicative identity? Is there anything we can multiply by A plus BI and not change it? 1, well, what if we do 1, 1? Let's see. So the A plus BI times 1 plus 1I, we get A minus B, and then plus A plus BI. So we don't get just A plus BI.
You have to put the I on there? Like what's the I, why do you have to keep the I?
Because I thought that's what you said. Didn't you say 1, 1?
So why do you have to keep, like 1 plus 1 and 1 plus 1I is different. So like why do you have to keep the I?
Oh, so 1 plus 1, wouldn't that be 2?
Oh, okay, that's what you're saying. Gotcha. Yeah.
So when you said 1 and 1, that's what I thought you were meaning. But 1 plus 1 would be 2. But why do we have to put the I? What if we don't put the I? What if we just look at 1? Or 1 plus 0I? What happens there if we multiply? A plus 0, 0 plus BI. 1 is of the right form to be in that set. So, in fact, any real number is of the right form to be in the complex numbers. It does, there's no restriction that B can't be 0, or that A can't be 0. Some books even make the distinction, if A is 0, they would call this an imaginary number, just strictly imaginary. B, 3I, 27I, strictly an imaginary number, as opposed to all the complexes, it's of a certain form. Do we think it's a field? Are there multiplicative inverses? Is there something we can take times A plus BI to get 1? With our usual multiplication, how do we normally write the inverse? What's the inverse, say, of 3? 1/3. What's the inverse of pi? 1 over pi. So normally, we say it's 1 over. The problem being 1 over A plus BI is not immediately in the right form. Anybody remember with complex numbers, if you've seen them before, you've probably done this, or even just other places. We typically don't like radicals in the denominator. So we try to rationalize. So we take this times the special form of 1, what's called the conjugate. And the reason the conjugate is helpful, if we just look at the denominator, I've got a squared minus b squared I, and then minus abi plus abi goes away. We did get rid of the radical in the denominator, and I've got a minus bi in the numerator. Two things we need to kind of watch out for here. Is it possible for the denominator to be 0? Under what circumstances is the denominator 0? If A and B are both 0. So 0 plus 0i doesn't have an inverse. Wait a minute, that's our 0. It didn't have to have an inverse if we're thinking field. What about anything else? Anything else, that denominator is not going to be 0. A squared plus b squared will not be 0 if we use anything other than 0, 0. Now, in its current form, it doesn't really look like this. Is there any way we can kind of rewrite that so maybe it does? What if I split it up into 2 fractions? And kind of rewrite some things. Would you agree those are the same?
Yes.
Okay, would you agree I now have it in the right form to realize, oh, that is a complex number. So that is a complex number. The complex numbers are a field. Everything has a multiplicative inverse. So, I'm out of time. I think we have finished up pretty much chapter 17, so you should be in a position to work through various problems, and those should be identified here in Blackboard as to the problems relating to chapter 17. Yes, so there are a number of problems there.
I'll see you at 10 too, though.